Okay, now that we've looked at some basic definitions for what an op-amp is, let's look at our first op-amp circuit. And I've drawn an op-amp circuit with an input source and with a couple of resistors included in the circuit. And there are a few things I want to point out about this op-amp circuit that you have not seen before, but which you're going to see a great deal more of. First of all, we note, and I've mentioned this before, that the power supply connections are not shown, but they are implied. If this were a real circuit, we would have to have a power supply. But as far as the analysis we're going to do is concerned, it's not necessary to worry about the power supplies. So they are going to be assumed but not shown. So that's the first thing. Now the second thing about this is we note that I've got 3 ground terminals in this schematic. This is actually very typical for the way people will represent electronic circuits. What we're trying to do is avoid having to run a long ground wire over the entire schematic and hooking everything to that long ground wire. Instead, there will be multiple grounds throughout the circuit schematic because it's neater to draw it that way. But the implied assumption is always going to be that these grounds are all connected together. So this is just a shortcut, and you will see more of this shortcut when we draw other schematics or other circuit schematics. So the voltages are all implied, and it's always going to be referenced with respect to ground, just to make things neater and easier. The third thing is that this op-amp circuit rather, has negative feedback. Now, negative feedback theory is far beyond the scope of this course. However, for us, it has a simple meaning, and we're just going to apply that meaning. And what negative feedback means is this: that we can trace a path through one or more circuit elements from the output to the inverting input. So that is all that negative feedback means to us. Can you go from the output and trace a path to the inverting input either through just a wire or a connection, a direct connection, or through one or more circuit elements? And in this case, we certainly can. I can trace from here through this resistor R2 into the inverting input. So this op-amp circuit has negative feedback, and in fact, every op-amp circuit we're going to look at in this particular course is going to have negative feedback. Now, you can absolutely make circuits with positive feedback using op-amps where we make a connection from the output to the non-inverting input. Those types of circuits are generally used for applications like memory circuits, multivibrators, oscillators, things like that. But once again, that's for more advanced courses. Here we're just going to assume everything has negative feedback, and therefore that's going to lead to some very useful properties that we're going to be able to see in all of the circuits we look at. Okay? So let's analyze this circuit. So you note I've got a input source here, VP, feeding into the non-inverting input. I've got, what we have here is really just a voltage divider. So from here to here, these two resistors form a voltage divider, taking the output voltage and then feeding part of it back to the inverting input through a voltage divider. Okay? So, given this negative feedback configuration, let's figure out how that circuit is going to work. Okay, so for the moment, I'm going to assume that this op-amp circuit internally is the same as that idealized dependent voltage source we talked about before. So there's a voltage source here internally, and that voltage source is the open loop gain times VP minus VN. So that's what's inside that op-amp, just that voltage source. So given that, let's write some equations. Okay, now first of all, given this idealized source, we know that the input currents to the op-amp must be equal to 0, because remember, with that simplified circuit, we just assumed we had just wires on the inside so that the dependent voltage source could reference those voltages. So the current must be equal to 0. They're just open, it's open circuit, just in the ends of wires inside the op-amp. So from this, I can now look at this and say, well, if this current's equal to 0, really this is nothing more than a voltage divider. I can write the nodal equation, but what I will get is that Vn must be equal to R1 over R1 plus R2 times VO. So this is just a voltage divider equation for Vn in terms of VO. I could, of course, go through and write the KCL equations through those two, write the KCL equation at the Vn node given these currents I've defined for those resistors. I could do that too, but I just wrote the equation directly instead. And if I write it this way, I can rearrange this, and I can rewrite this in terms of VO. VO is just equal to R1 plus R2 over R1 times Vn. All right, so these two equations, I'm relating the output voltage to the inverting input voltage. In addition, from the op-amp, we also know that VO must be equal to AOL times VP minus V sub n. Because, of course, this is just, as I said, a dependent voltage source, and we're going to later on assume A sub OL becomes very, very large. Okay, so given this, I'm going to substitute. Let's take this and let's substitute into here. And if I do that, I can rewrite this, and what I will get is that A sub OL times VP minus V sub n must be equal to R1 plus R2 over R1 times V sub n. And at this point, I can rearrange terms, and if I do that, what I'm going to get, I'm going to bring over all of the V sub n terms over to one side of the equation. So rearranging terms, what I'll get is the following. And so I get this expression. Where 1 plus R1 plus R2 over A sub OL times R1 multiplied times Vn is equal to Vp. So there were a couple of algebra steps going from here to get this. But I've now grouped all the V sub n terms on one side and the V sub p on the other. Okay, so if I look at this, now let's let the open loop gain get large. Let's let it go to infinity. As it goes to infinity, the denominator of this term here goes to 0. And therefore, what happens is that V sub n becomes equal to V sub p as the open loop gain goes to infinity. So this term goes to 0, so just 1 times V sub n is equal to V sub p. An interesting result. And what we find then is the potential at the inverting input must be equal to the potential at the non-inverting input. We give a name to this. We call this a virtual short circuit. So this op-amp circuit now has what we call a virtual short circuit. Vp and Vn have the same potential. The inputs have the same potential, but they're not physically connected together. So the two inputs now have the same potential without being connected together. This virtual short circuit is a consequence of two things: the negative feedback and the fact that the open loop gain goes to infinity, becomes very, very large. Now what you'll find in a real op-amp, the open loop gain is not infinity, but it's still very, very big, such that in a real op-amp, these voltages will be separated maybe by microvolts. There's a very, very small potential difference between the two. But as far as we're concerned, they're effectively at about the same voltage, and we're going to treat them that way from an ideal point of view. All right? Now, to have a virtual short circuit, we must have negative feedback. Always remember that. So if we remove the negative feedback, the virtual short circuit doesn't hold anymore. So the negative feedback and an open loop gain dependent voltage source here with AOL goes to infinity, those two things are a requirement. Okay, so given this virtual short circuit, given the fact I've got 0 amps flowing into the input of the op-amp, assuming it's ideal, and given the fact I am going to treat the output of the op-amp as if it were a dependent voltage source, all of those things together lead to what we call the 3 rules of op-amp analysis. So what are the three rules of ideal op-amp analysis? Well, assuming we're dealing with ideal op-amps, which is what we're mainly going to be doing, first rule, VP must be equal to V sub n. This is assuming negative feedback. Second rule is we assume the input currents are equal to 0. Third rule, the output node of the op-amp is treated as if it were a dependent voltage source. Therefore, it's defined, and therefore we do not need a KCL equation for the output node. So since V sub O, the output voltage, is treated as if that output node is connected to a dependent voltage source, then V sub O is a defined node. Whenever you have a voltage source, independent or dependent, connect a node to ground, then that node is defined. And since it's a defined node, what do we know about defined nodes from nodal analysis? You don't need to write KCL. You do not need to write a KCL equation for them in order to solve the circuit. So you do not write a KCL equation at the output node unless you define the current variable for the op-amp output. What do I mean by that? Just this. The output of the op-amp looks like a dependent voltage source. There's my output. If I'm going to write a KCL equation at this node, and I've got other elements connected to the output, then if I'm going to write that KCL equation, I better define that current I sub O, which is flowing through that dependent voltage source. If I don't do that, I will not solve my problem correctly. So, guess what one of the most common mistakes students will make when they are trying to solve op-amp problems is they'll try to violate rule number 3. Don't write a KCL equation at the output node unless you need to know the current that's actually flowing out of the output of the op-amp. Straightforward, but lots of people will make that mistake. Okay, these 3 rules all arise from me using that simple op-amp model that I just previously drew and assuming that we have some kind of circuit that causes a negative feedback. So given that, let's take these 3 rules and let's apply them to an example. Okay, so in this case, we've got ourselves an op-amp circuit. I've got R sub L connected from the output to ground. I've got these two resistors connected from the output to the inverting input, and then from this source to that input. And I've also got two input voltage sources, VA and VB. So let's go through and let us apply the three rules and figure out what the output voltage is. What is VO for this circuit? Okay. Well, let's apply the three rules. First of all, VP is equal to VN. All right. I've got negative feedback. Notice there's a path from the output to the inverting input. So I know that these two inputs must have the same potential if this op-amp is ideal. What is that potential? Well, I know that in this case, VP must be 2 volts. It's defined. It's directly connected to that non-inverting input. And therefore, Vn, V sub n must be equal to 2 volts as well. So I've got 2 volts of that input. Both inputs have the same potential. Rule number 2. I know the input currents into the op-amp must be equal to 0. Now let's go through and let's write any KCL equation we can for this circuit, making sure we do not violate Rule 3. Okay? So, looking at this, what nodes do I have? Well, this node, of course, is defined by the voltage source. I don't need to write a KCL for that. The output node is defined because we're assuming the output of an op-amp is connected through a dependent voltage source. Don't need to worry about that. I can certainly write a KCL equation at the inverting node, however. So let's do that. So the inverting input node, I'm going to pick some current directions through these two resistors. This must be 1 volt. That node is defined. Now I can write my KCL. And so in this case, what I get is that 1 minus 2 divided by 25,000 must be equal to 2 minus V sub O divided by 100,000 plus 0. That current's equal to 0. So this must be equal to that plus that. I have one KCL equation, but only one unknown. And therefore, V sub O is equal to 6 volts. And there you go. Now, V sub O, could I write a KCL equation for V sub O? Well, sure I could. You can always write a KCL equation for a node even if it's defined. Let's do that. Let's write a KCL equation. If I'm going to write that KCL equation, what do I need to include? I better include that current I sub O. So I need to include the output current of the op-amp. And so therefore what I get is that 2 minus V sub O divided by 100,000 must be equal, plus I sub O, both going into the node, must be equal to VO over 10,000. So I can now take this equation. Notice I've added a second KCL equation, but I've also added a second variable. So now if I solve this, what I will get is that I sub O will be equal to 560 microamps. So once again, this is optional KCL. Add a defined node. So my output node is defined. And so therefore, I don't need to write that, but if I do need to write that KCL equation or do choose to write it, I'm doing it to find I sub O. So I'm adding a KCL equation, but I'm also adding an extra variable. But just to find the output voltage itself, all I really needed was the KCL equation at that inverting node. So watch out for that. Like I said, this rule is violated all the time. And what I mean by that is I will see so many students who will do this. They'll say, Dr. Holman, I need to write a KCL equation at this node. And they'll say 2 minus VO over 100K must be equal to VO over 10K. Which of course is completely incorrect. They forget to include that current variable. They've now added an inconsistent equation, and then they tell me my calculator's not working or mathematics is not working. Well, you're right. You can't solve the system of equations when you've added this incorrect equation. So that's what you have to watch out for. Don't violate this rule, rule number 3, unless you intend to find out what that output current is that's flowing out of the op amp. Okay? Now something else I want to point out. When I calculated V sub O, you notice the 25,000 ohm resistance and the 100,000 ohm resistance were in this equation, but not the 10K. Which when you think about it is not surprising because we're treating the output of the op amp as if it were a dependent voltage source. So me adding a resistance to ground across a voltage source isn't going to change the value of that voltage. So we find something very interesting. We note that the value of VO is independent of that load resistance. Turns out that is a very important property of op amps. And in fact, it's one of the reasons why people like to use op amps, because of the fact that the output voltage, even in real op amps, is to a large extent can be made independent over a wide range of load resistances. So that turns out to be very, very handy in a lot of designs, and we'll in fact look at one of those later on. Okay? So, those are the 3 rules we need. You're going to be using those 3 rules of op amp analysis for every op amp circuit you're going to be looking at from now on. So use them well. Don't forget any of them. As long as you remember those three rules and apply them correctly, there's no circuit that I can give you or that you'll see that you will not be able to solve. So next time, let's start looking at some different configurations of op amp circuits, see how they work, and kind of start looking at broader classifications. And the first thing we're going to look at next time will be the inverting amplifier.